In the last lecture, we discussed the center of mass of a system of particles or of rigid bodies. We found that there is a point in an extended body where we can assume the whole mass of the body to be concentrated, so that the effect of external forces can be taken if the whole body is removed and only the center of mass with the mass equal to the mass of the whole body is left behind. In this lecture, we take another important concept, angular momentum. You see, you are familiar with linear momentum, which m v. V is the velocity, mass m is the mass, linear momentum is m v. Angular momentum is the counterpart of momentum or analog of momentum in rotational motion. In linear motion, we have linear momentum. In rotational motion, we have angular momentum. Linear momentum is a vector, we all know. It is a product of mass and linear velocity vector. The magnitude of the linear momentum is simply m v. The analog of mass in rotational motion is moment of inertia. I will discuss the moment of inertia in a moment, but the mass is replaced by moment of inertia when we consider a rotating body, and the velocity is replaced by the angular velocity. So, that what we have is p equal to m v in linear motion, and it is replaced by L equal to I omega, where L is called the angular momentum. We have just found this by translating linear momentum to angular momentum, velocity to angular velocity, and mass to moment of inertia. The magnitude of the angular momentum of mass m rotating in a circle of radius r, as shown here, is L equal to I omega. I is m r squared, omega is v by r, therefore, it is equal to m r v or equal to m r squared omega, depending upon which formula you prefer. And from this L, the magnitude L equal to m r v, we can guess what the vector form of L would be, and this form is m r crossed v, cross product of vectors r and v multiplied by m, or the cross product of vectors r and p. That is the form of mathematical expression of the angular momentum. So, angular momentum is m r crossed v. Therefore, you must be familiar with the cross product, and here I give you the way in which we can find out the direction of the angular momentum. What is known as right hand screw, and if you take a right hand screw and screw it like this, that is clockwise, it goes down. If you screw it like this, then it comes up. You must have this experience of a right hand screw. You screw it like this, it goes down, and if you screw it like this, it goes up. And this right hand screw rule we use to find the direction of the cross product of vectors. Here in this case, v is in this direction, r is in this direction. So, for the cross product, we have v in this direction, r in that direction, and r crossed v from r to v. So, we rotate with the right hand this way, and you can see the screw is going down. So, the vector L goes down. If you change the direction of r or v as here, then the angular momentum vector goes out of this plane of v and r. So, with the help of this right hand screw rule, we can find out the direction of the angular momentum, which is the cross product of r and p. In a rigid body, it is very simple. You have a particle I here, and r I is its distance from the axis of rotation, and therefore, we can write the angular momentum as m I r I in cross v I. V I is the velocity of this ith particle, and you substitute the value of v I as r I omega, and we get omega times m I r I squared, which is nothing but moment of inertia. Therefore, the angular momentum is moment of inertia times the angular velocity. In general, the angular momentum is not parallel to omega, but that is for higher classes. At this stage we assume that they are parallel. Actually, in a rigid body there are 3 axes about which if we rotate, then the vectors L and omega, they are parallel. Let us see, in the linear motion, if we apply a force, then we can change the linear momentum. Here, if we want to change the angular momentum, we have to apply what is known as a torque. Let us see what the torque is. Here is a rigid body rotating about the axis of rotation, which is outside the plane of the screen, and F is the force which acts at this point at a distance r from the axis of rotation. The angle between r and F is theta, and this distance, perpendicular distance between the force and the axis of rotation, is r sin theta, and therefore the torque is defined as the product of the perpendicular distance from the axis of rotation of the force F multiplied by the force F itself. So, torque is r sin theta times F. If F is in the same line as r, then the torque is 0, because the cross product of r and F is 0. You see, we had r sin theta into F. You remember that from this we can take a cue, we can take a hint, and we can write torque as r vector crossed vector F. And once again, if you have the 2 vectors, you can find out the direction of the torque. If in this case F is like that, r is like this, so therefore r crossed F would be this way. That means the right hand screw, if we rotate this way, then it comes out of the plane. So, in this case the torque, vector torque, has the direction outside, out of the plane. If r and F are like this, then r crossed F, you can see, if I r crossed F, no, the screw goes down. So, the torque vector is going down perpendicular to the plane of r and F. Torque is always perpendicular to both r and F, because it is a cross product, and therefore, in this case as shown, it points downwards. Let us write down the expression for angular momentum once again. L vector is equal to r vector crossed with p vector. Let us differentiate this with respect to t. So, we get dl by dt is equal to r crossed dp by dt plus dr by dt crossed p. The second term is dr by dt, which is v. P also contains v, so it is v crossed v, which is 0. Therefore, dl by dt is simply r crossed dp by dt, and dp by dt is F. Therefore, dl by dt is r crossed F, which is torque. So, the rate of change of angular momentum is equal to the torque, and if there is no torque, there is no rate of change of momentum. That means angular momentum stays constant. That is the law of conservation of angular momentum, that if there is no torque acting on a rotating body, then its angular momentum stays constant. In the case of linear motion, you know, is the law of conservation of momentum. In that case, if there is no force acting on the system, then the momentum of the system remains constant. That is the law of conservation of momentum. Since angular momentum is expressed in terms of the moment of inertia, it is worthwhile to talk about moment of inertia very briefly. Moment of inertia, first of all, depends upon the axis of rotation. You change the axis of rotation, moment of inertia changes. It also depends upon the distribution of matter around the axis of rotation. If you change this distribution of matter around the axis of rotation, then the moment of inertia also changes. You can see that the upper one is a wax, and in the heart shape, here we have reshaped it the same amount of wax, and the distribution around the axis of rotation has changed. Therefore, its moment of inertia also has changed. So, moment of inertia is a function of 2 things: the axis of rotation and the distribution of matter around the axis of rotation. So, let us come back to the angular velocity and the angular momentum. L is I omega, and suppose now the distribution changes, and because of that moment of inertia changes. So, what happens to L? If L is to remain constant, if there is no torque acting, if L is to remain constant, that means omega must change. So, to conserve angular momentum, therefore, the angular velocity would change if there is a change in the distribution of matter around the axis of rotation. Let us see this very interesting example. You must have seen this map in your geography class. Here we have shown the currents in the atmosphere, the winds in the atmosphere, and these winds carry a large mass around the earth. So, the mass distribution therefore changes because of the wind flows. Also, there are currents in the seas, in the oceans, you know that. They also change the mass distribution around the axis of rotation of the earth. The result is that with these two changes, changes in the air masses and the changes in the water masses in the oceans, the moment of inertia of the earth changes. If the moment of inertia changes and the earth being an isolated body, its angular momentum must be conserved. Therefore, what happens? Omega must change, and if omega changes, that is the angular velocity of the earth around its axis changes, then the length of the day will change. And I have shown you here the length of the day on certain days, and you can see the amplitude. The amplitude is measured in milliseconds. It is roughly 1 millisecond or a few milliseconds every day, and this is sporadic, this is not regular, there is no pattern, and this is the change in the day because of the changes in the air masses or water masses in the earth and the change of mass distribution around the axis of rotation. Apart from these changes, there are also regular changes. When the earth was born about 5 billion years ago, it was rotating very fast, and then it slowed down slowly, and now its rotation is much slower than it was at that time, and therefore, the length of the day now is much longer than the length of the day when the earth was born. Another interesting phenomenon connected with the conservation of the angular momentum. Let us consider the earth moon system. The earth moon system is isolated, therefore, their angular momentum has to be conserved, and if the earth is slowing down, then the angular momentum of the earth has been decreasing, and since the total angular momentum must be conserved, that means the angular momentum of the moon revolving around the earth must be increasing. Let me repeat this. The earth is slowing down, therefore, its angular momentum is decreasing, but the angular momentum of the whole system must remain constant. Therefore, the angular momentum of the moon, the orbital angular momentum of the moon must increase. Let us see what is the consequence. I write down the orbital angular momentum of the moon as mass of the moon into r squared omega, where omega is the frequency of its revolution around the earth. You know, you are familiar with the tides on the earth. These tides, you know, are caused mainly by the moon, and these tides, they have sort of locked earth and moon. Moon has slowly slowed down in rotation, and today the time period of rotation of the moon is the same as the time period of its revolution, so that we see the same face of the moon all the time. Now, that means that because of this locking, because the moon is now facing us all the time, the same face towards us, there is no scope in the change of angular velocity. That is, omega cannot change, but L is increasing. So, what do? We must increase r, because mass of the moon cannot increase, so we must increase r. That means that the angular frequency of the moon cannot change. To conserve angular momentum, the distance between the earth and the moon must increase slowly, roughly 4 centimeters per year. You see, this is a very interesting consequence of the conservation of angular momentum, that the moon is going away from us at the rate of 4 centimeters per year. Yet another interesting consequence of the conservation of angular momentum is the occurrence of seasons on the earth. You might have been told wrongly, or you might have read somewhere, that the seasons on the earth are caused by the changing distance between the sun and the earth. That is wrong, because the distance changes very slightly over the whole year. The real reason is the conservation of angular momentum of the earth. if the angular momentum of the earth is conserved, it means that the axis of rotation always points in the same direction in space, because any torque on it would change the angular velocity and therefore the axis of rotation. If there is no torque acting on the earth, the angular momentum is conserved and the axis of rotation of the earth in space always points to the same direction. The result is this, I have shown here. Earth, as it goes around the sun, its axis always points in the same direction. This you have done in geography, but at that time you did not understand that this is a consequence of the conservation of angular momentum. Here is the earth in 4 positions, and you can see that the axis points in the same direction, and therefore the light of the sun falls the variable amount of heat that is received by various parts of the earth during the year. You can see here the lower part of the earth in the southern hemisphere receives more sunlight and therefore is hotter. Here the northern hemisphere receives more light from the sun, more heat from the sun, and therefore is hotter, and in between these two positions where the whole earth has almost the same temperature. So, the seasons, they change on the earth because of the conservation of angular momentum. Another important consequence is what is known as the second law of Kepler. What is the second law of Kepler? That if a planet is going around the sun, then the area traced out by this in a certain time must be equal to the area traced out by it in an equal time. So, if A, B, C, D are the positions, then the area of the planet around the sun, then area AOB must be equal to the area COD. This is what is known as the second law of Kepler. This you must have done in gravitation. Now, this is also a consequence of the conservation of angular momentum. Let me show you this. Here is the planet at the position P, this is the sun, and in a very short time it goes to Q, and if omega is the angular velocity, then the distance PQ is almost equal to omega times dt. And since although this is shown as very far apart, actually I have taken a very short distance. Therefore, this OP is equal to OQ, and both are equal to the radius of the orbit. And what is the area of this can be equated with the area of this triangle. Remember that we have taken the positions at a very short time interval from each other. And now, what is the area of this triangle? The area of this triangle, which is also area of OPQ, approximated OSQ. The area of this triangle is what? It's base times the perpendicular into half. And if you find the area, you find area is half QS into OR. QS itself is half OR omega dt into OR. So, it becomes half R squared omega. And what is R squared omega? If you remember, m R squared omega is the angular momentum. So, if I differentiate this with respect to t, dA by dt is half R squared omega, and half R squared omega is the angular momentum of the planet per unit mass. If I multiply by the mass, this becomes the angular momentum of the planet. And if it is conserved, then this quantity half R squared omega must remain constant, and this half R squared omega is the angular momentum, and this means dA by dt, that the area covered in a certain time must also be constant. That is the second law of Kepler, that the area, let me show you this, AOB covered in a certain time is equal to the area C covered in an equal time. So, in this talk we have talked of angular momentum and its conservation. Remember, angular momentum is a vector quantity. It is a product of two vectors r and p, and its direction is always perpendicular to the plane containing r and p. Whether it is pointing upwards or downwards would depend upon the directions of r and p. If you use the right hand screw rule, and if you go from r to p, and if you have to move this way, then the screw goes up, and the angular momentum also is perpendicular to the plane containing r and p. On the other hand, if you tighten the screw, if the motion from r to p is like tightening the screw, then it goes down. That means the angular momentum is perpendicular to the plane containing r and p, but is pointing downwards. Angular momentum is a very important concept. I have tried to clarify this concept by several natural phenomena and several examples. I hope you understand this. In the next lecture, we shall take up gravitation.